Students, so today let's begin with session 4 of the sequences chapter from BSc Mathematics paper 3 CBCS 2021 onwards, the new syllabus from 2020 onwards. Session 4 we are going to complete theorem 1, 2 and 3. In session Y the remaining 4 and 5 on sequences. These theorems are on sequences we are going to complete in session 4 and 5. So today let me start with session 4. So BSc Mathematics paper 3 sequences. Session 4 theorem 1. So the theorem statement tells that the limit of a convergent sequence is unique. This statement tells you that the limit of a convergent, if the sequence is convergent, then you are going to have the unique limit. So let us start the proof of this theorem. Now let this xn be a convergent sequence. What is this? This is a, you are considering this as a convergent sequence. Okay. Now here if limit n tending to infinity xn is L1 and we consider again limit n tending to infinity xn is L2, two limits. That means by contradiction we are trying to prove this. If limit n tending to infinity xn is L1 and xn is also L2, there are two limits it is converging. It is not converging to a unique limit. It is converging into two different limits L1 and L2. We will consider this and try to prove whether this is a contradiction, and finally L1 should be equal to L2 or L1 is not equal to L2. We will try to show that. Now here let us assume, what are we assuming? L1 is not equal to L2. We are assuming what? L1 is not equal to L2. That means there exists a real number k greater than 0 such that modulus of L1 minus L2 is equal to k. That means the difference between these two limits is k. They both are not equal. Okay. Since what do we know? Limit n tending to infinity xn is L. How do we know this? By definition of the limit. We know this by definition of the limit of the sequence. Then there exists m1 belonging to n such that modulus of xn minus L1 is less than k by 2. This is for all n greater than m1. Okay. Now x1 limit n tending to infinity xn is L1. So we are considering here modulus of xn minus L1 is less than k by 2. Similarly, if I consider limit n tending to infinity xn is L2, okay, then what is that? There exists m2 belonging to n such that modulus of xn minus L2 is less than k by 2. This is for all n greater than m2. So this is by definition. You are able to write these two definition part. Now let us take m. What is m? M is the maximum of m1 and m2. That means m exceeds both m1 and m2. M exceeds both m1 and m2. Now let me consider this equation as 1 and this as 2. Now from 1 and 2, what do we have? Modulus of xn minus L1 is less than k by 2. And modulus of xn minus L2 is less than k by 2. This is for all n greater than m. Since we have taken maximum, so n greater than m. Okay. Now let me consider what is L1 minus L2. Okay. If I consider this, I will be able to write this as, I am going to add and subtract xn for this. So what do I get? Xn minus L2 minus of xn minus L1. This minus into minus plus L1. This is minus L2. I am adding plus xn and minus xn both in the modulus side. So now by inequality I am able to write it as this is less than or equal to modulus of xn minus L2 plus modulus of xn minus L1. So what is this? Then it is actually less than k by 2 plus less than k by 2. We know it is less than k by 2. and less than k by 2. Therefore, it is plus. So, what is it? Less than k. This is for all n greater than or equal to m. What is this? Modulus of L1 minus L2 is less than k. But what is happening? It's contradicting the fact that whatever we have considered, L1 minus L2 is equal to k. It's a contradiction. This is a contradiction. Hence, the assumption whatever we considered is itself false. That is, the assumption L1 is not equal to L2 is false. And therefore, L1 should be equal to what? L2. And thus proves the theorem. So, this is the limit of a convergent sequence is unique. So, this proves the theorem, first theorem. Now, let's move on to theorem 2. What does the theorem 2 tell us? If limit n tending to infinity xn is L, then limit n tending to infinity modulus of xn is modulus of L. Then if xn is convergent, the sequence is convergent, so is the modulus of that xn is also, sequence of modulus of that is also convergent. So we need to prove this. So let's start proving this part, second theorem. Now by definition, what do I know? Limit n tending to infinity xn is L. This is for all epsilon greater than 0. That means for any small quantity epsilon, there exists m belonging to n such that modulus of xn minus L is less than epsilon. This is for all n greater than m. This is by definition. I am able to write this. Now in this, let me consider modulus of xn minus modulus of L will be less than or equal to modulus of xn minus L. And what do I know? Modulus of xn minus L is less than epsilon. This is for all n greater than m. Modulus of each quantity positive. Xn is a positive quantity, L is a positive quantity. So I am able to write this inequality. This is because of the inequality. I know modulus of A minus modulus of B is less than or equal to modulus of A minus B. By using this, I am able to write it. So now what do I understand here? Since this is less than epsilon, therefore limit n tending to infinity modulus of xn is equal to modulus of L. So this proves the theorem that modulus limit n tending to infinity, this also converges to modulus of L. This is theorem 2. Now let's move on to the last theorem, theorem 3. Every convergent sequence is bounded. So what does this tell you? Every convergent sequence is bounded. Let us take up this in the next session. This theorem I am going to prove in the next session, that is every convergent sequence is bounded. If possible, by the definition, whatever we have learned about the limit, about the sequence, about the boundedness, if you are able to prove this, take it as an assignment and try to prove. Otherwise, you can find the answer in my next session. Thank you.